Hello, everyone, and welcome. My name is Realtime. I'm a senior principal at Geosyntac Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. Today's webinar will consist of a brief overview of the two programs, followed by a technical presentation on DoD-funded research efforts related to the detection of submerged, unexploded ordnance in marine environments. The technical content will be presented by Dr. Timothy Marston from the Applied Physics Lab at the University of Washington. We will pause midway through Tim's presentation to answer questions and plan to conclude the webinar with a longer Q&A session. The next several slides provide instructions on how to optimize your webinar experience. If you have not done so already, please download Zoom at the link shown here and provide it to you in your webinar registration confirmation email. If you're unable to download Zoom, you can view the slides using a compatible internet browser such as Firefox, IE, or Edge, and by creating a free Zoom account. If you have difficulties viewing the slides or if your screen freezes, try keying Control and F5 to perform a hard refresh. If you are accessing the audio through your computer, click the arrow next to the Join Audio button, select Test Speaker and Microphone, and follow the prompts as they appear on your screen. If you continue to have difficulties, please call into the conference line shown here. You may also submit a comment using the chat box. Please use the chat box only for comments related to technical difficulties with Zoom. The Q&A option should be reserved for questions for the speakers. So please do not submit questions for the speakers using the chat function. In case of continued difficulties, just download a PDF of the slides from the webinar webpage and call into the conference line provided to you in your webinar registration confirmation email. Note that we will be live streaming the webinar on the SERDP and ESTCP YouTube channel, and the link is shown here. Just a few reminders, today's broadcast will be listen only. You may submit your questions by using the Q&A box on your screen. You do not need to wait until the Q&A sessions to submit your questions. We do encourage you to submit them as you think of them. And when you do submit your questions, just add your organization name at the end of your question so that we can properly identify it during the Q&A session. With that, I would like to introduce Dr. Dave Bradley, who is the SERDP and ESTCP Program Manager for Munitions Response. Dave's professional career includes U.S. Navy-supported research, laboratory directorship at the NATO Undersea Research Center in Italy, and research and academic activities at Pennsylvania State University's Applied Research Lab. An emeritus professor of acoustics, he is currently an APL University of Washington staff member assigned to the SERDP and ESTCP program office. And most notably, he is a fellow of the Acoustical Society and has both chaired society committees and served as president. Dave, the floor is yours.
Thanks, Rula. Welcome, everybody. I'm especially looking forward to an exciting presentation by Tim in just a couple of minutes. Laura, if we could go to the next slide, please. The total program is SERDP and ESTCP. It's a multi-agency U.S. government program, including Department of Defense, Department of Energy, and the Environmental Protection Agency. The operative words on this slide are at the near the bottom, and they are fundamental research and advanced technology. SERDP is probably for many of you what I would call an accelerated program in those areas. Next slide. The ESTCP program, which is the other half, has a keyword again near the bottom, middle bottom, which is transition technology. Again, compared to many programs you might be familiar with in the US that are sponsored by the US government, these programs for us tend to be accelerated in time. The other operative words for ESTCP are facilitation of regulatory acceptance for the work that we do. Next slide. There's 5 program areas which are listed here. The one that's appropriate for today is Munitions Response in the middle of this list. All have interactive pieces, and a split up from the viewpoint of looking at it from a programmatic perspective is relatively arbitrary. But if you get into the details, you will discover that there are significant thrust differences between them. Next slide. Munitions Response has 2 aspects. More historically, a lot of involvement in remediation of munitions found on land. Work continues, of course, because in this business, this kind of effort never stops, but it has more of a focus at this point. The current focus in time is listed here, as you see. And generally, it's underwater, but I'll let you read for yourself the 3 sort of major focus areas. Don't be misled by some short statements here. What I would call the bandwidth of munitions response is much broader than what you see here. Next slide. The webinar series is a continuing one, of course, and roughly speaking, there are about 2 per month. They're listed here for your convenience, and we'll move on to the next, and I believe the last slide for me. That's really a contact point. I don't believe it was mentioned earlier, but at the end of this webinar, there will be a pop-up survey. And if you have the time, please take it to fill it out, because we're always interested in feedback. With that, I'm very pleased to turn it over to Tim Marston.
Thank you so much, Dave. Just a quick introduction for Tim. He is a principal engineer at the Applied Physics Laboratory at the University of Washington. His research interests include acoustical signal analysis, remote sensing, synthetic aperture sonar processing, and machine learning. And before joining APL, Tim worked as a postdoc from 2009 to 2010 in the Department of Physics and Astronomy at Washington State University, where he used synthetic aperture techniques to analyze the acoustic response characteristics of submerged elastic structures. And then from 2010 to 2013, Tim worked at the Naval Surface Warfare Center, Panama City Division, where he focused on the application of synthetic aperture sonar to mine countermeasures and UXO remediation efforts. Tim earned his bachelor's degree in electrical engineering from Seattle Pacific University and his master's and doctoral degrees in acoustics from Pennsylvania State University. Tim, we're delighted to have you. Please go ahead.
Great, thank you, Rula. So this presentation is going to be an overview of some recent developments that we've made with the buried object scanning sonar that's mounted on the multi-sensor towbody designed at APL. And I will be using our recent results from our survey of the blind UXO testbed assembled by Pacific Northwest National Laboratories in Sequim Bay to serve as a springboard for discussion of these new capabilities and tools that are meant to streamline the process of moving from raw data capture to UXO detection and classification. Let's see. Move to the next slide here. There we go. Okay, so I'm going to start off with a brief background of what the multi-sensor towbody is, and what the BOSS is in SAS processing, and review what the Sequim Bay testbed was and what it was meant to enable us to test with the system. Then I'll go over some of the tools that we've developed for BOSS data processing, including our live visualization tool and our software toolkit that we use for post-processing to do things like re-navigation, synthetic aperture beamforming, mosaicing, region of interest detection, and volume visualization. And finally, I will end the talk with a classification exercise where I look at the data from Sequim Bay and we'll show the results of using the different tools that we've developed to perform classifications and result in a series of contact lists, a contact list of UXO that if we had to remediate the area, we could hand a diver potentially. So to begin with a review of the multi-sensor towbody, this was an APL design platform. It was designed around a McCartney Focus 3 towfish. That's this big black box cart looking thing in the pictures on the right. And there's a series of sensors mounted on it. Currently, this includes the EdgeTech 2205 dual frequency side scan sonar. This is to provide wide area, high resolution surveys of targets on the surface. And also the primary sensor that we're going to be discussing in this webinar, the buried object scanning sonar. And you can see that on the bottom of the towfish on the lower right photo here. And there's a series of sensors that are also on board that are meant to augment geopositioning and synthetic aperture beamforming. So this is kind of a high-level flowchart on this slide showing the different features that we will be discussing. So on the top left, we have the multi-sensor towbody. This has things like the buried object scanning sonar and the EdgeTech side scan sonar on it. It also includes an inertial navigation system and a Doppler velocimeter for positioning, a sound speed sensor. This not only helps the DVL, but helps us with SAS processing afterwards, and a pressure sensor, altimeter, and there's other things. It also has a dual GPS. So the information from these different sensors gets fed topside via TCP/IP to our live data visualizer. That's called MUSTLive. But it's also simultaneously being stored on an internal hard drive. And the data is pulled off at the end of a survey. And that's when we use our software toolkit to do our post-processing. And that will be the topic of the second half of this presentation. So the location that we were scanning was Sequim Bay. That's located in the northeast corner of the Olympic Peninsula. You can see the location in a series of zooms on the bottom here. The particular location of the testbed was in the northern portion of Sequim Bay. The color coding for the bottom two right images has to do with the sediment parameters, the grain size. This was predicted using a multi-beam sensor. And what you'll notice is on the bottom right where we see the testbed, we have the outline of the 100 meter by 100 meter box that comprises the testbed. And we also have a target calibration line. So Pacific Northwest National Laboratories placed 16 targets in unknown locations and in unknown burial states within the testbed, but they also provided the target calibration line south of the testbed, and they provided us with the UTM coordinates for each of those targets so that we could perform a pre-survey to be able to see what the acoustic response was of the different targets in that particular environment to aid us in searching for those targets in the testbed. The photo on the left here shows the different targets that were positioned in the testbed. You'll see on the top are our two favorite science targets, 2-to-1 aluminum cylinders. One of them is solid, one of them is hollow. We use these targets because we have very good predictive models for the acoustic response of these particular targets, and they serve in a sense as fiducials. So we should be able to find those targets We also have a series of different UXO ranging from 81mm mortars all the way up to 155mm, and a variety of clutter targets you can see, including things like cement blocks and crab traps. When we performed our survey, we tried to include angular diversity because the more looks that we can get at a target, the higher chances that we'll see important features that enable us to discriminate between UXO and clutter. So you'll see we have these 3 sets of tracks spaced 60 degrees apart. Each of the track lines is spaced 5 meters apart. Our sonar swath is about 15 meters when we're operating at 5 meters altitude. And this close spacing enables us not only to get angular diversity, but also grazing angle diversity, because when we scan along the paths at these tight spacings, we will encounter the target from both different aspects and different grazing angles. Now, the particular sonar technology we're leveraging is something called synthetic aperture sonar. The idea behind synthetic aperture sonar is that, especially for low frequencies, it can be difficult to mechanically make a large enough physical array to get high resolution. So instead of making one very large array, instead we work with a much smaller array and use the movement of the array to generate a synthetic aperture, where what we do is we keep track of signal phase and amplitude, and we keep track of the position of array as a function of history, and then we can back project the acoustic signal to reconstruct in this case, 3-dimensional reflectivity map. What makes the BOSS different from most synthetic aperture systems is that most synthetic aperture systems are side-looking systems. So they use a array that may be 30 elements in a long track dimension. We have a long skinny array that is pointed the same direction as the vehicle is going, and you can reconstruct a very large high resolution image at long ranges. In our present case, we are more focused on trying to find buried objects. And when you're looking off to the side, you run into problems, especially when you have a fast sediment, meaning the sound speed in the sediment is faster than the speed of water because of critical angle issues. Below certain angles, you just don't get a lot of acoustic signal penetrating into the sediment. And as a result, you can't see buried objects. So with the buried object scanning sonar, instead of having the standard synthetic aperture type of array, we have an across-track array. And we're looking down into the sediment. So we're really mostly focused in the region of grazing angles ranging from -30 degrees to +30 degrees. And as we move our system along, we're creating a 2-dimensional planar array that looks kind of like a ribbon, like you see in this image here. And with this ribbon, we can back project to generate a 3-dimensional volumetric image. Now, because we have an along track array, an actual mechanical along track array, you can kind of think of the BOSS as a large low frequency multi-beam that looks into the sediment. Every single ping we make, we can generate an image that doesn't have to be a synthetic aperture image. The drawback is that our source is an omnidirectional source, and so you have no long track resolution, and that's where the SAS processing comes in. So these 2 figures on the bottom show a maximum intensity projection through range for a volumetric image reconstructed on the top just using this multi-beam processing, where every single ping we're generating an image, but we haven't done any focusing in the long track direction. And what you'll see is some streaks here above these arrows, and those are target signatures for particularly bright targets. Now, following SAS processing, these collapse now to very distinct targets on the sediment. And we also get our SAS gain, an improvement in SNR, and we can see now small discrete objects scattered throughout the volume. Now, I mentioned we're dealing with volumetric images. Volumetric rendering is an entire field. There tends to be trade-offs in different visualization techniques. We're, of course, looking at data on a flat screen, but we're dealing with a volume. So there are a number of ways that you can render effectively 3-dimensional volumes. It turns out one of the quickest and most effective ways is simply to take a 3-dimensional volume and represent the scattering or the features in that volume by computing maxima through each of the three orthogonal directions representing the volume, and representing the volume as three separate images. So that's what I'm showing here for a particular scan in Sequim Bay. In this case, this is actually from the 2019 Sequim Bay survey. And I have three different representations of a target field. On the top, you have a Z-MIP, and a Z-MIP is where you are taking a maximum in the height direction. And so you can see this is kind of like looking down on the target field. On the bottom left, we have an eastings MIP. This 3D image was projected to georectified northings, eastings, and up coordinates. So if you look through the eastings, you can see the targets arrayed near the surface. Many of them are buried, some of them are proud. And on the bottom right, you see the maximum intensity projection through northings. One of the drawbacks of MIPS is, especially for acoustic imaging, is if you have a bright layer several meters down below the surface, then when you take a MIP through the Z dimension, sometimes that bright layer will completely hide any of the lower scattering strength targets near the surface. So one of the things that we do, and this is especially true in the live visualization tool, is that we provide the ability to range gate so that you can cut out layers that could potentially hide targets when you're looking at a Z-MIP through a volume. Now this is a more detailed flowchart of the different processing that we do on the system, including live processing, which is in the box on the right, and post-processing. And don't be put off by the apparent complexity of this. All this is actually quite intuitive when you see the processes that we'll be discussing later. But for the moment, I'm going to focus on the live processing, which is shown in the red box here. But to back up, why do we do live visualization in the first place? When you're doing UXO surveys, the timeline isn't quite as important as doing something like, say, mine countermeasures, where how long things take is extremely important. With UXO, we could take a day or two to perform post-processing to try to really maximize the quality and performance of, say, our target recognition efforts. However, when we are able to look at data as it's being acquired, what we have found so far for all of our deployments with the multi-sensor Towbody is that it's absolutely invaluable for determining sensor best practices. It's invaluable for determining how you should position your sensor, what altitude, when you should dive, what data you should look at in post-processing. It's helpful to have to only route through gigabytes instead of terabytes of data. We can do live target tagging. We can determine if we actually scanned a target that we were looking for. For example, in Lake Washington, we scanned an airplane. And because of our live visualization tool, we were able to see that airplane scrolling beneath the sonar, and we knew that we had acquired it. So our tool that we've developed for doing this is called MUSTLive. It enables sensor, target, and geographic feature positioning. It also shows streaming synthetic aperture MIPS, and it allows us to do various sensor and connection diagnostics as well. So on the next slide, I show the main window of the MUSTLive tool. It's meant to be very simple and intuitive. Currently, it's MATLAB based, but we have intentions to compile this to make an executable that you can run alongside EdgeTech's software to help control the boss. And you'll see there's a number of options here. For example, you can replay data as if it was streaming live, so you can familiarize yourself with the software and how it works, or you can do an actual live connection to the multi-sensor Towbody system. There's a number of presets that you can select if you want to do diagnostics, or you want to do synthetic aperture beamforming, or you just want to look at the real or raw data. It also allows you to select the host port and address. And there's a nice big run button for when you want to start. The second slide shows all the beamforming options. So the beamforming, how you set the parameters makes a big difference on the kind of features that you can observe. So for example, you can set the number of pings in the queue for integration. We can support about up to 350 for live processing, and we can set the integration angle. This could span from 20 degrees to 60 degrees, depending on the sample rate, what kind of integration angle the sample rate supports without aliasing. And on the last panel here, this shows the type of data products that the user wants to be able to display. So for example, you can display diagnostics information, mapping and vehicle pose information, or real aperture data or synthetic aperture data. If you select one of the presets, it automatically selects all of these options for you, or you can make a manual setting depending on what you like to see. So for the Sequim Bay experiment, these were the data displays that I was most frequently using. I'll go into several of these in more detail, but on the left you can see various mapping and pose display information. On the right we have our streaming waterfall of SAS data and a real aperture profile on the bottom left, and a connection diagnostics window on the bottom. So taking a closer look at the streaming SAS data, there's two views that we most commonly look at. We can also include the third, which is the long track MIP, but I don't find that quite as useful for live target tagging. On the top is the ZMIP, so that's looking straight down on the target field, and on the bottom is the side view that looks through the column as a profile. You'll also notice these red bars. These red bars are user defined. You can define the width with the numerical field down here, and you can define its vertical position with the scroll bar. This determines the range over which the ZMIP is computed. So for example, if you have a bright layer and you want to trim that layer out of your observations so they don't hide targets near the surface, you can select a narrow range and set the position just to straddle, say, the top layer, and it will filter out layer information that you want to reject. There's also a save button. If you see a target of interest, you can click that save button and it will export the current figure on the screen. Plus, it will also dump a map file that includes all of the navigation data so that you can go back and reconstruct from the data your observations at the given time that you observed anything on the screen. This is the map window. This allows you to see where your vehicle is at the present time, plus its history. The history is color encoded based on the vehicle depth. When it's on the surface and it's acquiring GPS data, the color turns white. You'll also notice these green circles. These are waypoints that you can add using an external text file. Right now I have these waypoints set to mark the corners of the test bed so that we know when we're entering the test bed. And also I have the waypoints set to show the different locations provided by PNNL for the calibration field. And what this allows us to do is when we're crossing, for example, the target field, we know that we should be observing something in the SAS window. Additionally, you could potentially use this to mark out areas where, say, there's a float and you want to avoid that with your towfish. You'll also notice there are 3 rings around the current location. These are spaced 5 meters apart, 5, 10, and 15 meters. The outer ring you can change the radius of using the numeric field or these plus and minus buttons. And what that allows you to do is, say you want to know when you're 100 meters away from the box, or you want to know when you're 50 meters away from the calibration line, you can set that to give you a visual indication. On the right, we have navigation and environment data like the vehicle speed and the sound speed in the water. Also the time submerged and the distance submerged since GPS has been acquired. And this is important because our navigation system uses dead reckoning. It integrates a DVL with an inertial navigation system. And so, of course, we're integrating velocity to get position. And as we stay underwater for longer periods of time, our position uncertainty grows. So using the information over here, you can intuitively estimate whether or not you're 5 meters within where your sensor currently believes you are, or maybe 1 meter or 10 meters. This is the orientation window. The box inside the ring here will mimic the towfish's yaw, pitch, and heading, and also to some extent the current amount of heave that it's undergoing. You can also see on the right there is a history of the heading, and on the bottom is the water column profile. So you can see the vehicle diving here, and you get the same color coding representing depth. You can also see where the sediment is relative to the surface and the towfish's current position. So in this slide, if you can see this movie, this is a movie showing the SAS processor in action. One of the things I'll point out first off is that the SAS data doesn't make a lot of sense at the moment. And this is because we are pinging extremely quickly. We're pinging at 60 Hertz. And when we are not close to the sediment, it's out of range. And the SAS processing range migration arcs aren't correct. But once we get to a close enough altitude to the sediment, and now the sediment is in view and we're not looking at, say, the previous third or fourth ping, then the SAS beamforming works correctly, and you can see targets if they appear in the field of view of the sonar. On the left, on the top, you can see the map view. The outer ring has been expanded so that we know we're within 50 meters of the target field. And on the bottom left, you can see the orientation window. Now we're back on the surface. The little grid underneath the towfish is the surface, and it's moving at the same speed relative to the towfish as you would expect. And you can see now we're diving. And this is just a helpful tool to enable you to know what the vehicle is doing on the surface. And on the right, we have our connection diagnostics. So the connection diagnostics show if the sensing or the sensing modality, the beamforming modality that you have selected is overburdening the graphics processing unit. So for example, if your ping difference is consistently popping up to 3 or 4, then you know that your system is lagging and you're not keeping up with the speed of the data as it's being broadcast over TCP/IP. So that covers the live processing capabilities. And what I'm going to do right now is stop, and if anybody has any questions concerning the material we've already covered, I will take them.
Great, thank you so much, Tim. And just a reminder for everyone, you may submit questions by using the Q&A box on your screen. So we did receive 10 questions here. We'll try and get through a few and then allow you to finish your presentation, Tim. So starting with a question from LBNL, could you comment on the accuracy of geographical positioning of UXOs?
Yes, in fact, I have a whole section on that coming up in the next half of this presentation. But in short, the raw output from the inertial navigation system has a fairly high amount of variance. But when we do some post-processing techniques, we have 2 stages of post-processing. The first stage of post-processing that we apply to the inertial navigation system tends to bring us within the distribution peak tends to be about 1 meter in precision, and the sort of center of the distribution happens to be consistently about 1 meter from the UTM locations that PNNL gave us for their targets. We can further reduce the variance using another technique that I will describe later in the presentation. Thank you for the question.
Thank you, Tim. What is the water depth limitation for the system, if any? And are there sediment types or are there any sediment type restrictions?
That's a great question. So currently, I believe that our main limitation for how deep we can go is the cable length on our towfish. I think the system is specified to 100 meters currently, although there, I believe, is plans to make that go much deeper. But for our system, I'm not entirely sure if we can support much greater than that given the current cable length. But I don't think that there's anything inherently limiting us to 100 meters from an engineering standpoint. I think that could be expanded, but I'm not the right person to ask about that. If you contact me afterwards, I can get you in touch with people who would give you more information about that. Regarding the sediment, there are certainly some sediments that appear more transparent than others. So for example, when we were in Lake Washington, we saw probably 4 or 5 different layers, and we could see literally 13 meters into the sediment down to the bedrock. And I will show some examples of this later. In Sequim Bay, there were several different environments, and some of them we could see more deeply into, and others, the attenuation seemed much more rapid. I believe that with most of this area that we were seeing, we could probably see over the test bed several meters into the sediment. Again, I have a particular figure that I will show later in this presentation that shows some sediment transition boundaries, and you can see the effects of different types of sediments on our ability to peer into them. Some sediments, if you have gas, for example, near the surface, are almost acoustically opaque, but we didn't run into any of those in this particular experiment, and those are kind of a special case.
Great, thank you, Tim. This is a question from the Lincoln Lab at MIT. How long does it take to cover a 100-meter by 100-meter test site?
So that really depends on how many angles you want, and probably also depends to some extent on the number of times you've deployed the vessel and how experienced you are with the system. So we spent 4 days doing our survey because we had 3 different looks and we had an extremely tight line spacing. But I don't think it has to take that long. And the area coverage rate, if, for example, you're trying to do a 100 by 100 meter patch, is going to be less efficient than if you're doing a larger area and you can have, for example, longer runs. So I'm going to hold off on putting a specific number on that, simply because that really depends on the kind of survey you want to do. We covered the entire 100 meter by 100 meter box probably in 4 or 5 hours with a tight line spacing just on the first day, but of course we wanted to get multiple aspects. So yeah, it really depends on what kind of survey operation you want to do.
Thank you so much. We've got a few questions coming in from overseas. The first one from the Netherlands. Is there a minimum vertical elevation required for the towfish?
A minimum vertical displacement.
Altitude, yep.
Yeah, so I would say that's probably based on how comfortable you are potentially letting your system crash into the sediment. I think we really didn't take the system much lower than 3 meters, but I don't think there's anything limiting you from the standpoint of will the system work if it's 1 meter over the sediment. I think it will. The altimeter, you know, maybe the altimeter will throw a fit. I don't know. But we typically operated at 5 meters, and we tried not to go much below that.
Thank you, Tim. And these are 2 questions from Germany. First, what is the frequency range that can be emitted by the eBOSS? And second, are you using automated pre-processing algorithms to enhance diffractions from objects?
I'm sorry, what was that second part? Automated what?
Automated pre-processing algorithms to enhance diffractions from objects. For example, in case you have strong reflectors.
Yeah, okay, great, thank you. Okay, so the frequency range that we are currently using is 5 kilohertz to about 23. And that is with a bit of pre-whitening thrown in there, and part of the top of the band has been cut off because it looks like there's a little bit of communications noise or some kind of noise that bleeds into the sensor at the top end that contributes to some imaging noise. Regarding the pre-processing, there are a number of different things you can do. I tend to reserve the more complex stuff for the post-processing. For example, I have a process called spatially variant apodization that gets rid of side lobes, or at least reduces them. There are a number of nonlinear operators you can use. For the live streaming stuff, it's really just a bit of pre-whitening, pulse compression, and standard beamforming though.
Great, thank you, Tim. This next question is from EPA. Have you conducted any tests with small munitions, 20 millimeter to 40 millimeter range?
Not yet, no.
Are you planning to?
Well, you know, I think that's a great idea. I think it's definitely worth doing. And maybe it really depends on what people consider to be an important part of targets in the test bed. I'm confident that, you know, if SERDP is interested in being able to detect and classify those kind of targets, that they will be included in future test beds, but they were not included in the test bed that we surveyed.
Thank you so much. This next question is from the Hawaii State Department of Health. Have you tested your approach on rocky bottoms and reefs, or only on sediment? Currently only on sediment, but I would love the chance to test this on a rocky bottom or on coral. I think that would be a great opportunity. Great, thank you, Tim. This is another question from the Netherlands. Would it be possible to attach your system on a working class ROV to operate in zero speed conditions and in salt water? So the eBOSS, I believe, has already been attached to different UUVs in the past. As far as putting on an ROV, there's really there's nothing preventing beamforming of the sort that I'm showing from being applied on an ROV. There's no problem with that, as long as for SAS, all of the appropriate sample rates have been met to perform back projection without aliasing, and you have enough accuracy in your array location that you can beamform without causing significant errors due to mismodeling the array. So I don't see any inherent reason why the eBOSS couldn't be put on an ROV. Great, thank you. Another question from LBNL. Is the PNNL testbed site a standard demonstration site, and how can we find more information about it? So the Sequim Bay testbed, as far as I understand, and I don't want to speak for PNNL here, and if you wanted to find out more, you could contact me or Kevin Williams at APL, and he could get you in contact with the people at PNNL who are in charge of the test bed. But I believe this was a demonstration test bed just to demonstrate the fact that they have the capabilities to make a blind test bed, and to sort of serve as a first initial test to see how well these test beds work for evaluating different types of UXO detection technologies. But I don't believe the test bed that we surveyed is some sort of official test bed that SERDP is using to formally evaluate UXO detection technology yet. I think PNNL may have that responsibility at some point, but I'm not sure. And I could put you in contact with the people who do know the answer to that question if you contact me after the presentation. Thank you, Tim. One last question, and then we'll let you finish your presentations and and then we'll answer any remaining questions towards the end. This is from the Woods Hole Oceanographic Institution. If the target field contained dispersed clutter objects, such as large cobble of the order of the test cylinders, would these be immediately differentiated from the UXO target? So I would say that probably depends on what feature space you're looking at the targets in. I think, you know, when you're looking at features, there are certain distinctive things about UXO that you really don't find in natural objects very frequently. For example, a long straight edge followed by a particular taper with a flat side on the other side. You know, there are some shape features that seem to give UXO away. However, a lot of the recent effort in things like acoustic response as a function of angle modeling or acoustic color modeling, that's meant to enable you to use the acoustic response of things like UXO to differentiate them from, say, a similarly sized rock.
And I don't currently have in my post-processing toolbox any sort of robustly developed target recognition algorithm that's been plugged in to enable you to easily do that kind of discrimination beyond simple, looking at the data and trying to use various features that from past experience to differentiate. But I believe that is one of the main goals of a lot of the research that's been done in the acoustic arena here for UXO detection and classification, is to use the acoustic response to be able to do that kind of quick discrimination between clutter and targets.
Wonderful session, Tim. We're going to go ahead and ask you to please continue with your presentation.
Great, thank you. Okay, so this next half is going to cover the post-processing tools that enable us to take the data from the vehicle and map them to georectified coordinates, make mosaics, and extract regions of interest and do volume visualization so that you can perform some sort of target classification. And as that recent question pointed out, it's important to be able to distinguish targets from similarly sized clutter. And there is work going on that is meant to enable that type of discrimination as well. So the work I'm going to be talking about is described in the red box here. I'll go into more detail on this. The idea behind the eBOSS software toolkit, which is the post-processing set of tools that we use to go from raw data to target characterization, is that you can do all of these different tasks: re-navigation, mosaicing, beamforming, in a very simple manner. Eventually, we want to be able to compile all of this into a single program that makes all of this intuitive and simple. This is still a work in development, so currently everything is a set of MATLAB scripts, but the end goal is to get something compiled here that will be usable by a broader user base. So I'm going to start off this post-processing chain of events with re-navigation. And this is really speaking towards that question I had earlier about geolocation accuracy. So one of the issues that you have with an inertial navigation system is that when you're out of contact with the GPS systems, then you have no more absolute position reference available. And when we're underwater, now you could use a USBL or something, but we don't have a USBL. So when we're underwater, our system for positioning relies on dead reckoning. We have a Doppler velocimeter, and we have all of the accelerations and orientations from a fiber optic gyro. And as we progress underwater, the system could be extremely accurate, but because we have to integrate velocity to get position, our position uncertainty is going to increase the longer we are underwater. And inevitably what happens is eventually we've done our scan and we come back to the surface, and the GPS system gets acquired. And that's what I'm showing here in this figure, is we've come to the surface, and then once we have these little white rings around the positions, that means that the system is receiving GPS, and the Kalman filter inside the inertial navigation system is going to say, oh, I've got GPS signals now. I thought I was over here, but it turns out I'm 10 meters over here instead. And you're going to get this big discontinuity that doesn't represent in any way the sort of physical nature of how towfish respond. So if you, for example, look at the accelerometers and velocity measurements, they're going to be inconsistent with this big gap here. So even though the Kalman filter is giving you the most optimal estimate of where your position is at any particular time, it's not necessarily, it's still limited to causal relationships. However, following operations throughout the day, we can take all the state data from our inertial navigation system. This includes things like accelerations and velocities, GPS position estimates, and we can throw all of this into one big optimizer that strips causality. So now I'm allowed to use acceleration and velocity measurements and GPS measurements, both forward and backward in time, to give me the best position estimate for the vehicle at any given point in time. Further, we can constrain the behavior of the vehicle to act in some sort of physically realistic manner. So that's what we're doing in this optimizer that I call first stage renavigation. So in the next slide, you'll see what the navigation solution says happened following renavigation. So with the renavigation solution, you no longer have this big discontinuity, but instead you have some smooth behavior that takes the information from the GPS, but you can back propagate all of the position uncertainties to give you a much better solution in time prior to this GPS act. And this is a fairly robust process, and it gives you consistently and reliably better results as mosaicing goes, and it reduces both the risk of observations and their actual accuracy. But we even better if we use the acoustic data that we captured itself. So this is the second stage navigation, or feature-based renavigation. And we've also incorporated this. So, and this presupposes that we've done our beamforming and georectification, and I will discuss how we do that in a few slides. But the idea behind the feature-based navigation is we take the maps that we've generated using the multi-sensor towbody, and we solve for a navigation solution using, again, physical constraints for what the vehicle can physically do. And we've solved for a navigation solution that best lines up our observations of features on the seafloor. And this gives us a very precise, and I'm using precise intentionally, because if we don't have any sort of absolute reference underwater, it doesn't necessarily improve our accuracy a huge amount, but it does make all of our observations consistent with each other. So this gives us a very precise navigation solution that allows us to do things like combine mosaics using sums or maximum without causing artifacts because targets disperse from having poor local positioning precision. And I show that in a couple slides, an example of mosaicing with these different layers of precision. But one of the other cool things that feature-based navigation can do is allow you to quantify the improvements in positioning precision as a function of applying these different stages of renavigation. And that's what I'm showing in these plots here. So the top three-dimensional plots show the alignment error observed for each of the different stages. So on the left, we have just the raw out-of-the-box solution from the inertial navigation system. And we have displacements in the X direction and Y direction. And we get a quality value as well for each of our offset estimates, and that's the vertical axis. And what you'll see is for a quality of below about 6 or 7, we just get a random distribution with a radius of about 5 meters. However, above that, we start getting this, this point cloud. And what you'll notice about this point cloud is even though you have some sort of faintly tighter distribution around the z-axis, there's a huge amount of outliers around extending out to around 5 meters. And that's simply because I limited the search radius to 5 meters. For the renavigation solution, what we notice is that everything is much tighter distributed around the z-axis. And this is a major improvement. This means that our accuracy and our precision have both improved for this renavigation solution. And of course, for the feature-based navigation, because it's specifically trying to come up with a solution that tightens this around the z-axis, we get something that looks almost like a needle-like spike. And on the bottom, these two-dimensional plots simply show the absolute value of the displacement, so square root of x squared plus y squared, on the vertical axis and the quality on the right. And again, you see the spread decrease as we increase the number of renavigation operations. And this is a histogram of those. The point here is to show that the peak of the distribution for the raw out-of-the-box INS solution is at about 2 meters, but it's extremely heavy-tailed, meaning you have a lot of outliers. Whereas the renavigation solution, the peak is now at about 1 meter, but you also have a significantly less heavy-tailed distribution. And for the feature-based, everything is very tight, around 0 meters. That's simply because the alignment is basically below pixel level, below the resolution of the alignment operation. Now, this is the example of mosaicing with the different renavigations. This is first stage renavigation. What I've done here is taken all of the scans from all 4 days over the calibration line, and I'm projecting each of those scans onto a georectified grid. And then I'm taking a maxima through all of those different scans to create one single 2-dimensional image. And what you'll note is that the targets are positioned in the center of these circles, the little stars in the center of these circles. And these circles are 2-meter radii. And most of the targets end up being these tiny little constellations inside these yellow circles, indicating that, generally speaking, we're within 2 meters of where PNNL said the targets should be. However, we still have some dispersion due to this local inaccuracy. If, however, we now do the mosaic using our feature-based renavigation, all of these collapse now to well-focused targets. And furthermore, not only do the targets come into focus, but you can also see now we can observe well-focused background texture for the sediment as well. Now, the mapping, of course, presupposes that we have performed some sort of imaging operation. So that's what we have our SAS beamformer for. And I mentioned how SAS beamforming works a little earlier. Instead of raw back projection, we use something called fast factorized back projection in our current implementation. It's GPU accelerated. And it has a number of options, like it allows you to again, change the maximum number of pings that can be integrated and the integration angles. And this is an example here of one of the files that have been beamformed to the southeast, I believe, of the test bed. If you recall from one of the earlier slides showing the Sequim Bay map, there appeared to be some greenish coloring off to the side of the test bed. That meant that there was finer silt-like texture. Now, if you look in this image here, you'll notice that there is a very stark sediment transition. However, the sediment transition that happens to be so abrupt also happens to be about 2 or 3 meters below the surface of below the sediment water interface. Furthermore, so the vehicle is moving from left to right, and the sediment on the right is representative of the type of sediment that was present in the target field. On the left, we had that more silty sediment, and you can see we can see a longer ways through it, and there appears about 3 meters down some much brighter sediment. Another interesting thing about whatever this layer is down below is it doesn't have an extremely flat boundary between it and whatever is above it. So you'll see lots of stuff suspended in this sediment volume, and we don't get a strong specular reflection. Unlike in Lake Washington, where we could see multiple layers, almost all the layers in Lake Washington seemed to have pretty smooth boundaries, which meant you would get something like a coherent specular glint every time we hit another boundary. We don't get a strong specular glint. In fact, I don't think we get any specular glint from this lower layer. Now, I mentioned specular glints. These can be a major problem when you're trying to spot targets. The idea behind a specular glint being, we have an omnidirectional source above a smooth, flat reflector, which is the sediment water boundary. That reflector is going to have some very tight directivity pattern, and our array happens to be right in the middle of that main lobe that describes the backscattering response of this interface. And that results in a very bright specular glint right below the array. And that is simultaneously one of the most distracting and bright things in the imagery when you're beamforming, but also it can hide targets. And I have an example here. I searched through the data to find instances of when we went right on top of different targets. So on the to left here, we have some targets that are proud. You can still see them because they're very bright above the specular glint. But these third and fourth from left were flush buried right at the surface, and the specular glint makes them very hard to detect. And on the right, there's another target that's a little bit buried, and you can't see that target at all. So what do we do about the specular glint? It turns out it's coherent, and you can detect it. So we have a detector that we've integrated into our beamformer that finds this glint and attempts to filter it out without affecting the backscattering from UXO scale objects. So you can see here, following the specular deglinting, we can see the targets just fine, but the specular glint has been removed. And this is really one of the enabling factors for getting feature-based alignment to work, because if you don't filter out the specular glint, then it tends to form an artificial feature that can disrupt the feature-based alignment process. Now, every time we beamform these objects, we end up with a huge three-dimensional array. The size is typically around 3,500 by 300 by 800 pixels. And if you want to write a 3D array to hard drive that's that large, it takes a long time. It's multiple gigabytes. And if you're writing, say, to an external spinning drive, it takes a long time just to pull a single image off of the hard drive if you want to query it. So instead of saving these three-dimensional volumes, because they're very fast to compute using this post-processing GPU-accelerated beamformer, instead, what we do is we do a surface detection, and based around where the surface is, we take strips that are 40 centimeters thick, and we take maxima through those. So we take maximum intensity projections through these different layers, and we characterize the most salient scatterers in some volume just as a set of these layer MIPS relative to the surface. And we also save a full Z-MIP through the entire sediment volume as well. So we save, we describe each of these files, each of these volumes just as a set of MIPS. Really saves on the size of data that we have to store on the hard drive. And we also save the associated navigation data so that we can prescribe for every single pixel in the MIP a georectified location. And this enables us to georectify these to make mosaics. So that's the next stage in the eBOSS processing toolkit is the tool for mosaicing. With the mosaics, we take all of the different MIPS through these layers that we've collected for all the different files that we've processed, and we georectify them, and then we combine them to form a single map of the area that we scanned. And we're currently combining these scans using the maximum operation. The reason I'm doing that is because it's convenient and doesn't show a huge amount of artifacts. It turns out there's better ways of doing this. For example, a weighted power sum. I have a paper that's several years old now that shows that if you tune the power of your power sum, you can draw out different types of features, different types of scattering features in an environment. So that's a goal in the future, is to implement different ways of combining the different observations of the sediment, but right now I'm just using a maximum intensity projection. So keep that in mind when you view the following examples. But now I'm going to go through a few example mosaics that were generated for Sequim Bay. And each of these mosaics represents a combination of all of our observations, but at different depths relative to the surface. So this is from layer 6 of the set of MIPS that we've collected for each of our scans. This layer is below the surface. It ranges from just below the surface to about ½ meter deep. And so everything that you see on here corresponds to some buried object. Now, it's a little difficult to see if you're looking on a small screen here, but one feature, for example, that you can detect if you're looking at this is right where the cursor is located. There's a long, skinny object that's about, I think, 2 meters long, maybe it's 1.5 meters long, and this is fully buried. Now, when I flip to the next slide, you'll see that that object disappears because it's buried and isn't present near the surface. So that object disappeared, but instead now we have 3 bright objects, and this because this layer now shows proud and flush buried things. So we have new features. Some of the buried features disappeared. Some proud features now appear. And in the next layer, which is only proud objects, so now we're skimming the top, going to a ways above the top. Now we really see proud objects, and we don't see much else. So these different layers allow you to highlight different types of targets. And for example, if you had a very bright layer that you wanted to reject in your map, you can do that simply by shifting between these layers. Also, for completeness, we have a full Z MIP. This goes through the entire sediment volume. So now you see that long skinny object, but you also see these different objects near the surface. This is great for Sequim Bay because we didn't have a very strong secondary layer beneath that we could detect. However, in a place like Lake Washington, this might not be ideal. Another thing to note here is that if we had not done the specular glint processing, this whole thing becomes a huge crosshatch of primarily of specular glints. But when you get rid of the specular glints, now you can start seeing things like sediment texture and targets much more easily. Okay, so once we have a mosaic, the idea is we want to find regions in the mosaic that we think may potentially contain a target so that we can extract the information in that region, process it to maximum quality, and do things like volume rendering or acoustic color processing, any sort of feature extraction that you may want to do either for human-based target classification or for acoustic color or target recognition algorithms to be able to queue off of. So for that purpose, we developed the ROI data extraction tool. And what this tool does is it allows you to look at the mosaic and select regions of interest and tell the computer to beamform these. And that's what I'm showing here in this window. So this is the main window of the ROI selection tool. This allows you to zoom in, zoom out, change the color limits. If you click on the layer button down here on the bottom right, you can use your scroll bar to quickly flip between layers. So you can compare, for example, features that you see on the surface to right below the surface, and you can change the color map. And if you click the select button, your cursor will become a crosshair and you can select the item that you want to query. Once you've made your selection, if that's one selection or 30 selections, you can hit beamform. And what the software does is it routes through all of the data files associated with the mosaic, and it determines which ones were in, which ones contained acoustic data that captured the regions that you selected. So it filters out all of the extraneous files, the ones that didn't insonify the targets that were selected. And then it goes and it beamforms using each of those different observations, and it creates volumetric images plus all of the associated metadata for the vehicle motion, position, and environment measurements like sound speed, and it stores those in a ordered mat structure that we can write to disk. So once we have the region of interest data for all of these sets, of course, the next thing is we want to be able to manipulate them so we can determine if they contain a UXO or a clutter object. So that's what we have our ROI visualization tools for. And the next couple slides are going to show those. So the first thing we want to be able to do is take any of the targets that we selected and view each of the different looks at that target. So that's what the full set of MIPS tool does. You can see here the output from running that tool on a particular target captured and saved to disk. You'll see the target location shown here relative to its position in the larger mosaic. And each of these rows or each of these columns shows the same target from a different pass around the target. So for example, this left column shows a particular look at that target through Z, through eastings, through northings, and through phi. The phi is a special case because for each of these targets, there are two volumes that are rendered. One is in Cartesian coordinates, georectified Cartesian coordinates, and another is in a path-centric cylindrical coordinate coordinate system. The reason for that is because if you use a cylindrical coordinate system based on the path of the vehicle, if you take a maximum through the angular dimension, the image you get is almost identical to what you would have observed if you had used a standard two-dimensional synthetic aperture sonar. And this is handy if you want to do, for example, dimensionality reduction on acoustic color features. So that's what this bottom set is here, where we're taking the Cartesian coordinate representation, we're computing the acoustic color representation, and we're doing some filtering operations. And this gives us a two-dimensional acoustic color feature representation where the horizontal axis is SAS angle, the vertical axis is frequency, And that's the normal representation that thus far people have mostly developed target recognition tools to work with. So the idea here is a dimensionality reduction operation from 3 dimensions to 2 dimensions to hopefully facilitate plugging in extant target recognition algorithms. Now, the 3 orthogonal views can sometimes be kind of limiting. So that's what this next tool is developed for. So this allows you to, again, query any of the targets that have been beamformed. And what it will do is this leverages MATLAB's internal volume renderer. Since I think 2018, it's included a volume renderer that works quite decently. And this will show simultaneously all of the different looks at the target, and it also provides this viewpoint manipulation window. And this viewpoint manipulation window serves kind of as a trackball. So this box is kind of like a trackball. You can drag this box around, and as you drag this around, all of the viewpoints of these different regions of interest will simultaneously update, allowing you to change your perspective of observation of any of these individual looks. And this is useful because every time you take a look at these targets and you're looking at it from a different aspect, you highlight different features. And some of them are not best viewed using the northings or eastings or Z-MIPS. You'll also notice this last window here looks a little different. That's because this last figure is an intensity sum of all of the other representations. And this is useful only because of the high precision of the feature-based navigation. If we hadn't done that, or it hadn't worked very well, what we would have seen is a nonsensical agglomeration of different edges and features in here. But because of the high precision of that feature-based renavigation, now all of the different features that we observe from different angles are positioned geometrically accurately relative to each other. So what we're almost seeing here is something kind of like a circular synthetic aperture sonar intensity sum, if you're familiar with circular synthetic aperture technology. Now the next couple slides show viewpoint changes. So you can see what I'm doing now is I'm dragging the box upward, and the perspectives mirror the changes, and now it'll drag left, and this just shows some of the operation here when you're dragging that box around. We have another volume visualization tool that we've developed in this project. This one does not use MATLAB's internal renderer. And this one, instead of using a maximum, uses alpha blending or transparency. So this is just another volume rendering technique. It gives you, it has pluses and minuses relative to maximum intensity projections. One of the problem with maximum intensity projections is that you completely lose a sense of depth. And furthermore, faint scatterers tend to be overwhelmed by larger scatterers, and alpha blending doesn't have that same problem. One of the limitations you'll find on almost all available volume renderers, whether it's WA3D or you're using MATLAB's internal renderer, or you have some dedicated, say, a medical community renderer, is almost none of them allow you to completely decouple a voxel's intensity from its color and its transparency. You may find some tools that allow you to get, say, 2 of the 3 decoupled, but I haven't found any that allow you to decouple all 3. And this is specifically what VoxView is designed to do. And the reason you want to do that in some cases is because you may want to combine other types of information other than intensity in an image. And a color channel or an alpha channel allows you to combine more information into a single plot than, say, simply intensity. So here's an example of another type of data visualization with VoxView. That previous one here was from Sequim Bay of a target in a muddy region where the color encoding shows depth relative to the surface. This is simply locking color to intensity, but we have 2 linked views where if you change the viewpoint on one, it changes the viewpoint on the other, and these are 2 linked domains. So the domain on the right is the 3-dimensional acoustic spectrum captured for the target, and on the left is the spatial domain representation. So those are some of the tools. I don't have time to go through all of them, but the idea now is to do a demonstration for the Sequim Bay UXO testbed. So the idea here is I'm going to use the tools that I've shown, the mosaicing tool, the region of interest selection, and all of these region of interest query and visualization tools to perform my own UXO classification task for the UXO testbed. And I'd like to preface this saying my guesses for the UXO testbed don't represent APLs in general. I've done this mostly just to demonstrate how efficient this process is and how simple it is. So to begin, taking the region of interest selection tool and looking through the various layers at Sequim Bay, I made 24 manual detections. These were just based on how bright I thought an object was against the background. I set my threshold pretty high. There were a lot of objects that potentially could have been UXO that I didn't select here, but these were the most salient objects that I would say, you know, if I were trying to clean up a site and I had to limit my number of selections, I would have chose these. So I made 24 manual detections. And after doing this and hitting Beamform, the software comes back and says, there were 98 contributing scans, meaning 98 files that we had collected that have acoustic data pertaining to these different locations. Now, because some scans see multiple targets, we get more looks at targets than the number of scans. So the program also says we have 271 different looks at all of these targets, or different acoustic observations of these different objects. And from these 271 looks, for each look, we're going to generate 2 volumes. We're going to generate one in Cartesian, and we're going to generate one in cylindrical coordinates. So from these 24 detections, we have 542 volumes that we're going to beamform, and the total computation time for this, thanks to graphics processing units, was only 28 minutes. And following that, if you take all of the different image observations and you combine them in one big intensity. So this is like that last image in the V-Link set that I showed earlier. So now we're combining all of our different looks at the targets. And now I'm showing the full array of the different selections here. So instead of being different looks at the same target, these are the intensity sums for each of the different targets that I queried in that first region of interest selection. You'll see that some stand out against the background really strongly. For example, this one in the top right, and others, for example, this whole bottom row, the relative scattering strength of the object I selected compared to the background is much smaller. So I'm not going to go through the entire process of looking through the full set of MIPS and using V-Link and perhaps looking at the three-dimensional acoustic color to try to determine which these different objects are. However, some of them stand out almost immediately as far as ease of identification. For example, most of us at APL who have participated in the Gulf of Mexico experiments, for example, BayX, T-Rex, GulfX, we have seen probably hundreds of acoustic color responses for hollow cylinders. And there was one particular target out in Sequim Bay that when we look at the acoustic color, it's like, oh yeah, that looks like the hollow cylinder. Furthermore, if you do the intensity combination and you look down the axis, it even looks like a hollow cylinder. You get this nice circular outline, and it looks like there isn't really anything in the middle. So I'm pretty sure we know where the hollow cylinder is. Same with the solid cylinder. We've seen the acoustic response of that a bunch of times. I'm fairly confident I know where the solid cylinder is. The scuba tank as well, and the cinder block. The cinder block's a funny one because when I show this image, it doesn't look anything like a cinder block. However, as I'll show on the next slide, if you look at the full set of MIPS, this is a good example of when the intensity sum is not helpful. There are certain looks at the target which show very clear features that are hidden when you combine it with all the other looks. Also, some of the objects out there are almost immediately recognizable as UXO. For example, this one on the top left here, you get a straight edge with a curve on the front, and you'll also see the same thing for these other plots here. Now, one of the things you'll notice is that behind the straight edge and the curve, there appears to be smudged information. A lot of that smudged information, my guess is probably elastic features. In other words, you may have some spatial manifestations of things like Rayleigh waves or flexural modes that get excited, and those show up as defocused energy trailing behind the leading edge from a specular glint, typically in imagery. Now I mentioned this, the sender block was an example of when an intensity sum is not that useful. I'm showing some examples here of particular snapshots from the full set of MIPS that are useful for identifying the cinder block. Of course, we're not trying to find cinder blocks, but it's also just as useful to be able to positively rule something out that's a bright scatterer as well. So with the cinder block, we have this view that I call the tape cassette view here. It looks like a rectangle with two little blobs. And my guess is this probably comes from scattering from the chambers in the cinder block. And you get this really nice compact flat surface as well. So I'm fairly confident, again, that we know where some of the clutter objects are that they positioned, and we can rule those out. So going through each one of these targets and classifying them on a scale from 1 to 10, where 1 is I am positively sure this is not a UXO, and 10 is I am entirely sure this is a UXO, and 5 would be I am on the fence. I've made this map for each of the different objects. And if it's above a 6 or 7, it's going to be orange or red. So all of the red dots are things that I'm quite confident are UXO. Of course, I don't have the answer key, so I'm not sure, but I'm quite confident. If someone said, Tim, you have to clean up this site, tell the diver where they should look, these are the coordinates I would provide. Also, some of these are clutter items that we can positively identify. So bringing up the items that I showed before, I'm fairly sure the hollow cylinder is up here. The solid cylinder is down here, along with the scuba tank, and the cinder block is over here. Now you'll notice there are several items that I'm kind of on the fence about. This one in particular is quite buried. So the next plot shows a burial depth description. So in this plot, I have green representing fully proud, yellow is flush, and red is buried. And I have the UXO, the things identified as UXO, labeled in boxes. What you'll notice is that the one that I showed on the previous slide that I was pretty unsure about, it also happens to be a very small object, so if it was a UXO, it would be a pretty small UXO, is buried, and this one happens to be buried about ½ meter deep. There's another UXO up here that's also buried. This one's only about 20 or 30 centimeters deep. Now, it may not be a UXO, but I'm labeling it as a UXO. I would say if I had to remediate this area, that it was certainly worth checking out. This one is also fully buried. So just because something's buried doesn't mean you don't get features that could cue you into it being a UXO. But when something does get buried, the SNR also tends to deteriorate a bit. And that is also a major function of, for example, the type of sediment that it's in. For example, when we did the Sequim Bay experiments in 2019, and we had some targets in a siltier sediment, we saw them extremely clearly, even when they were quite buried. So we get burial depth information, and we have a location of points that, that we could tell someone to go down and investigate for further remediation. Now, the point of that, again, I don't know the answer key, so I don't know necessarily how well we did. However, and it looks like I have to finish up here. But the point of this was that whole timeline was very, very short. It took me about 2 hours, including a lunch break, to go from the mosaic all the way to making classifications. And the idea here is to really make the must have some tools that open it up to a broader community for doing UXO and remediation work. And to give time for questions, I'm going to skip the conclusions. I would, however, like to acknowledge Kevin Williams and also Dan Plotnick, who is originally was part of this project, and the APL Ocean Engineering staff for all their hard work on the MUST, as well as EdgeTech for their incredible support, and PNNL for making the testbed. So now I will open it up for questions.
Great, thank you so much, Tim. We really appreciate it. I want to remind everyone that Tim's slides are available for download on his SERDP and ESTCP webinar webpage, and the video will be available in a few days. And you could always reach out to Tim at the email provided on the slide prior to this if you have additional questions. But we do have some questions I'd like to get to today. We're going to start with one from Washington State University. Tim, how do you combine information with must height control in practice?
Okay, so I'm sorry, I missed that second part again. Combine information with what?
Must height control in practice.
Okay, how do we combine information with must height control? That's an interesting question. I'm not entirely sure I understand it. If this is a motion compensation question, the beamformer incorporates the motion estimates from the inertial navigation system. It turns out that this is really the apertures that we use for the BOSS are much shorter than most of the apertures we use for, say, long-range SAS imaging. Furthermore, the frequency content is much lower, so the wavelengths are longer, and so we have a bit more tolerance for things like navigation error. So what I do is I take the inertial navigation system data, and because it tends to have a little more variance than we know the system has to have because of inertia, I filter it through a hydrodynamic model for the vehicle, and then I use that as the basis for all subsequent SAS processing. If your question meant something else, feel free to contact me afterwards. I'd be happy to address further.
That should be fairly easy to do given who's asking the question. All right, this next question is from the Applied Research Lab at the University of Hawaii. How did you determine what to use for the thickness of the MIPS layers?
Okay, so for the thickness of the what layer?
MIPS. M-I-P-S.
Oh, thank you. Okay, MIPS, for the thickness of the MIPS layer. Okay, so that was all just heuristics. I felt like 40 centimeters was on the size of a target. If I had a layer that was 40 centimeters, I also provided some overlap between them. So the layers that I showed were completely separated, but I have half a layer overlap between layers with the idea that we don't want to completely miss anything. So when you scroll through, you can see different features on these different layers without ever missing a target. That could be adjusted, however. That's customizable.
Great, thank you. And one last question before we wrap up from the Great Lakes Dredge and Dock Company. What is the time frame for post-processing typically? And without an ultra-short baseline position system, do you find it difficult, or do you expect it to be difficult to revisit targets to perform multiple passes?
So that's a great question. Regarding the multiple passes without a USBL, I think that really depends on how long you intend to stay underwater and what the accuracy of your navigation system is. For example, there are a lot of systems out there. In fact, we're going to install one soon that should have about 0.2, 0.3% distance traveled accuracy. And if you're underwater for, say, a kilometer, that's going to be 2 or 3 meters error as you progress underwater. And that's really not too bad. That's much smaller than the swath width. So you should be able to position your sensor so that you recapture something if you're only underwater for say a kilometer. If you're underwater for 3 kilometers, then that could start posing a problem. And this is where you would start changing your concept of operations for how you use your system, depending on what you know the uncertainties are. A USBL could be something that would be very helpful for getting accurate position accuracy. However, when you're 100 meters away, I don't entirely know how accurate a USBL necessarily is. That's not a technology I'm super familiar with. But because the error grows without bound as you're underwater, undoubtedly a USBL would eventually be a great help if you wanted to do, for example, a many kilometer long survey.
Great, thank you so much, Tim, again, for an outstanding webinar and a very engaging discussion. We apologize for not getting to all of your questions, but again, feel free to refer to the slides and to the video recording that will be available shortly. I would like to remind everyone that our next webinar is on Thursday, February 25th in the Environmental Restoration Program area. This webinar will focus on DoD-funded research efforts to biologically treat chlorinated solvents and one for dioxane in groundwater. This webinar will feature two speakers, Dr. Shelley Mahendra from the University of California, Los Angeles, and Mr. David Lippincott from Aptum Federal Services. Registration is open, so please visit the SERDP and ESTCP webinar webpage to register for this and other future webinars. Before we conclude, I would like to ask for your assistance in completing a very short survey that will pop up on your screen at this time. This concludes today's webcast. Thank you so much for your time.